Okay, so thanks everyone for coming. Today I'm going to talk to you about a really exciting use case that we've been working on for the last almost a year. And last year I gave a talk at BitCom titled Towards Quantum Utility in the energy sector. And today I'm happy to share some interesting scientific results where it's really pushing quantum advantage, actually, for a real-world business use case. So just to set the stage a little bit about E.ON. So maybe not everyone's heard of E.ON before. We're one of the largest utility and energy providers in all of Europe. So we deliver energy to about 47 million customers. We're active in over 15 different countries in Europe. We manage 1.6 million kilometers of power lines across Europe, and we have about 1 million connected renewable energy assets in Germany alone. And this video here on the right-hand side is a video I love. This basically shows the yellow dots are the amount of local renewable energy being generated, and red is the energy demand in different counties in a region in Germany. And what you see is that actually the power grid is a living, breathing system. So what you want to do is, when you move to a sort of digitalized grid where we don't have single combined heat and power plants generating electricity, we want to leverage all of this renewable energy being made everywhere. So now you have millions of in-feeds injecting local renewable energy in the low voltage grid. And this is a very difficult challenge in order to schedule and optimize this usage. At E.ON, we call ourselves the playmakers, of the energy transition. So we want to lead the way in sort of innovative solutions to drive this kind of sustainable energy adoption across Europe. And for our quantum team, our ambition is to explore and unleash this potential of a new technology. And this kind of all started in 2019. We started a very small quantum team. It was just on the side at the time. So we've been doing it for some time now. We've partnered with IBM Quantum, so we have direct access to their systems, as well as their team from IBM Research across the globe. And we also are a direct customer of D-Wave. And internally, we have a team of full-time staff working on this. A small team, but we also supervise master's and PhD students through academic alliances and things like this. And there's lots of different things you can do with quantum. And here, I just want to kind of show three main areas that we think we can apply quantum. So we're not really big into kind of material science and those traditional use cases where people think the first evidence of quantum advantage will be. We're looking more into combinatorial optimization, quantum machine learning, and also system and scenario modeling. So this is things like energy contract pricing, Monte Carlo simulation, and things like this, because energy is procured in a stock market, in the energy market. And so these are the three main categories we've strategically looked at. And we see the QPU as just sort of one subset of how we'll use it in a fully integrated stack, where we use neurons, so for AI, and then you have classical bits and you have quantum bits. I want to start by telling the story about what kind of problems should you look at if you're doing optimization about finding quantum advantage. So how do you start there? So this slide is taken or inspired from the IBM working group for quantum optimization. And what you can see here is, if you imagine all the set of the problems, you have classically easy problems, and a subset of that is classically hard. And what do we actually use in the real world? This is the practically relevant sphere, okay? And some things are hard, some things are easy, but ideally, we all want to work with not just math problems, actual real-world stuff, yeah? So if you have this, in the center now comes quantum advantage. So you can get quantum advantage. So right now, there's hints of this where people are looking from this direction. This is a math driven approach. These are abstract, fake data sets that mean nothing in the real world, but they're hard enough, and it's good enough to prove a quantum advantage, and that's what everyone's trying to do right now. And that's fantastic for the whole field. But the steps are, you start with a hard problem you know, you check for quantum advantage, and then you check to see if it's useful in the real world. Ideally, the other direction is a use case-driven approach. So this is where we want to come from the bottom, where we start with a business use case, and we want to check for, is this problem hard enough? Should you even use quantum for it? Most of the time, no, actually. Yeah? And then finally, if you can use quantum, can you even get a quantum advantage? And I'm going to tell you about a use case. I never talked about it before publicly, but this is a very nice use case. This is a collaboration we've been doing with IBM Research in Dublin, Ireland, as well as the Hartree Center in the UK. And the use case is about peer-to-peer energy trading. So go back to what I showed you earlier with the yellow dots, yeah? So local renewable energy. If you have solar panels on your roof, if you imagine this is your local neighborhood, and some people here have their solar panels, and there's a battery here, and you have an electric car plugged in maybe, and you have maybe a solar farm plugged into your local neighborhood. What you want to do is basically trade this locally generated electricity. So if we zoom in the literature, there's two layers to this problem. The first is called the physical layer, and this is where you have the actual power lines, and you have the houses connected to the grid. And on top of this, you have what's called the virtual layer. And the virtual layer is in the cloud, and this is where you have each house has a smart meter. And from these smart meters, this is where you do the individual transactions. So in the billing system, you basically have, so house 2 is trading electricity for money, yeah, to the different neighbors. So in this case, the neighbor with the solar panel is giving a little bit of electricity out to his neighbors because they have demand. But also in another short time interval later, he might give a bit of electricity or bill it for a certain price in an automatic system to another neighbor. So if everyone gets this, this is the core concept. Now let's generalize it. If you start with more neighbors now, it's not just looking at can you trade a little bit to him or her, it's actually quite a complex system. Everyone with solar or a car plugged in theory, can trade with each other. So what you have is this complex little graph I've drawn where you have different amounts of energy that there's supply and demand between all these houses, okay? So now you see the combinatorial explosion about how difficult this problem can get at scale. Many, many, many possibilities. And the problem is, you take this energy demand and you want to decompose it into trades. So here is one instance of time in the first 15 minutes. You might have these two trades between these neighbors. And the next 15 minutes, you might have these two trades for these other two neighbors, and et cetera. And what you want to do is split this total energy demand into the minimum amount of simultaneous transactions. So you're satisfying all of the energy demand you're making, people need it, and people can generate it. And how do you share it in the shortest amount of steps? Okay? Now the deep mathematical connection here is these are actually matrices. So you can describe the demand matrix. It's called the doubly stochastic matrix, and this is what it is on the left-hand side. And on the right-hand side, these are known as permutation matrices. And this is where now it gets interesting from a quantum perspective. Step 2 is check for hardness. This is a fantastic paper. If people are not aware of it, I want to plug it here. So this is the quantum optimization benchmarking library. There's an open source GitLab repo, as well as a paper here, where we and the collaborators identified 10 different hard mathematical problems that can be, in principle, written as a QUBO and run on a quantum computer. And we have instances there that are either unsolved to optimality or in general unsolved. They're hard problems. And this is supposed to be the foundation for proving quantum advantage. So you have a set of really hard problems. And one of these problems is exactly, spoiler, it's exactly what we were looking at. So there's one problem called the minimum Birkhoff decomposition. So this is the nerdiest slide I have. We ignore the math, but if you look at the blocks, the matrices, they're kind of similar to what I showed earlier. So here you have a demand matrix, and you see the problem is how do you split it into these binary matrices such that you split it into the minimum amount of those binary matrices. And this is an extremely hard problem. It's one of the hardest problems in the paper. If you look at the runtime for the dimension, so how many peer-to-peers you have, even for 3 and 4 people, the runtime, if you run with Cplex, is about 15 minutes if it's a dense graph here. Even if it's sparse, it scales exponentially. So this is a good starting point. We know that this is a hard problem. And now comes the third step. So check for quantum advantage. So can we use quantum computers not to directly solve the full problem, but instead can we leverage their solution variety as a strength to provide a quantum advantage? And this is a bit of an unusual way to solve the optimization problem, because most people write a QBO, you throw it in, boom, done. You run QAOA or quantum annealing, whatever. So here we're trying to do something a little bit different. Can we use samples of solution to somehow come up with a better solution in the end? And there is a precedent for this. So in quantum chemistry, there's a new hybrid algorithm called sample-based quantum diagonalization. So those who do material science probably have heard of this before. And the idea is basically you can leverage a quantum computer in a hybrid fashion, combined with a supercomputer to basically sample the solutions that the quantum computer gives you and post-process that in the supercomputer. And so we wanted to take this idea and extend it to our optimization problem for this solution. So on a very high level, we start with the demand matrix. So this is the local energy demand here. The next step is we sample solutions from the quantum computer. And here you can see a couple different solutions. Then we check if any of these samples actually produce better decomposition splits. So you can see that we have the original thing is sort of a sum of different samples. And then finally, we want to keep the good samples and update the remaining demand. So you sort of subtract what's already been traded. So you start with your demand, and then we would subtract a good sample, and this results in a new demand. We're hard to see, but now 0.6 turns to 0.2, 0.4 turns to 0.1. So now you have a new demand matrix, and then you keep the process going. And the idea at the end is you want to basically get 0 everywhere. So you've established all the trades. And finally, the results. So we proved rigorously that our quantum sample-based heuristics outperforms the best classical solvers known to date for this particular problem. So here's an example of a graph size. So the current best one that exists in the literature is called the fully corrective Frank-Wolf algorithm. So FCFW is the orange dots. And on this axis, you see how many decompositions are there. And lower is better. And what you can see is for the number of people involved in the peer-to-peer trading, the best one is the red here. So the red is our extended algorithm that uses QAOA as a subroutine. And you can see that this is the lowest dot, basically. And we can take this a bit further, so we can run this on real IBM quantum hardware. And here, this plot is a little bit technical, but basically lower is better. It's D is your original demand matrix, and X is your new one. So you want this to be as close to 0 as possible to say you're doing all the trades. And here's your decomposition length, so how many elements are in the kind of sum to do the actual trades. And what you can see here is in the original FCFW classical, we have orange, which only got to here. And then we have another version of simulated annealing, classically. It's a little bit better. Run on real quantum hardware at the utility scale. In the end, used 78 qubits, 79 qubits. On IBM Kingston, we get a bit further down. But at the end, we can still simulate it using MPS, which is a classical method or quantum-inspired. So it's not quite quantum advantage yet, but probably with a bit better hardware and a larger problem instance, then we should be in the regime where we can't get this blue line anymore, which is the classical simulation of our quantum algorithm. Our paper came out this morning on the archive. So late, actually, that this QR code just goes to archive with my name searched. So just click the first paper there. And it's called Boosting Sparsity and Graph Decompositions with QAOA Sampling. And lastly, feel free to connect on LinkedIn. There's the link to the benchmarking paper. And yeah, many thanks to the fantastic collaborators that I work with from E.ON, Hartree Center, STFC, and IBM Quantum. So George, Naime, Oscar, Francesca, Stefano, Giorgio, and Victor. And yeah, thank you very much.